Can you hear me? Great. Okay, so in this set of slides, we're going to run through some examples, and some of you have noticed that I am leaving out some of the details, and that's true. It is in the code, but I will give you more details as we get closer to the break, where you're going to have to do some of these, or if you want to. So example 6 is, so I teach a class where I go through a whole bunch of different software with my students. It's the class I'm thinking of is a Python class, and we do this iris classification problem. It's a classic problem. And so I thought, well, this iris classification problem that I do with my students, I wonder if I could do that on sheaf. And so what I'm doing is I'm stealing the data from this other package. So if you see in the beginning of the code, there's a whole bunch of manipulation. It's just that I'm trying to mangle the data into a format that I can use sheaves to deal with it. And so that's why I'm installing scikit-learn and all that stuff. It's just to grab that data set. And so this data set has, well, like it has 4 different numerical columns. So for each observation, it's one of 3 different kinds of iris, one of 3 different species. And then there are 4 different measurements made on that plant. And then there's 150 observations. So what you typically do when you do a classification problem is you randomly split the data into training and testing, which we do. We'll do that. And you can do it in whatever ratio you select. You can do like a 10-90 split or a 30-70, whatever you pick. It doesn't matter. Okay. And you can use a specific random seed if you want to reproduce the results. And I found that different random seeds give me really good results. But to be fair, I picked a random seed would give me typical results. Okay, so some of my takeaways from this example is to show you that sometimes you can harness sheaves to do something that honestly you should use different software. But let's say the software doesn't exist yet. Maybe you're going to write it in the future. You want something to get you started. You want something to just get your feet wet, get started so you can get some initial results, and then you move from there. Sometimes you get lucky, and sheaves just do the whole thing beautifully. Michael has an example where he was working with some people, and he's like, let me just try this on sheaves, and his sheaves outperformed the software they were using. So that's magic. But that's not the expected value. Expected value is it's a rapid prototyping tool, gets you started, gets you some initial answers, and then you're going to go ahead and build something that's better or find something that's more suited to your problem. So it can work out either way. Okay. Oh, and just because you're using sheaves, you won't magically have a good model. You can still make a bad model in sheaves, which I'm going to do. Okay, so so this is just an example. If you have, these are our PCA variables, so they're kind of amalgamated variables. The way the actual software works is it just, this is what the way the groupings will look in those variable spaces. Okay, so just so you get an idea that these species should be pretty easy to tell apart, but right here on the boundary between these 2 species, there's some overlap. So we're going to see that when we do this with my naive model. So what I'm going to do is I'm going to take the training data and I'm going to create 1 sheaf per species. So my species is a categorical data, and I'm like, I really wanted this example because I wanted categorical data and numerical data in the same problem. So I said, okay, I'm going to just actually make a sheaf with my training data for each species. So each of the 3 species has its own separate sheaf. And these are just your boring star-shaped sheaves, the same way you did, linear regression or something like that. Okay, we're just finding the average value in that 4-dimensional space. Very basic sheaf. By that point, it's boring. Okay, well, what I'm going to do is one at a time, I'm going to introduce the new thing I'm trying to test, the new plant, the new observation. And I'm going to see when I add it to the first sheaf, when I add it to the second sheaf, when I add it to the third sheaf, I'm going to see a change in the consistency radius. And whichever one gives me the least change in the consistency radius, I'm going to say, I think that's the home for that. That's where it probably belongs. Okay. And of course, I would expect most of my errors to be between the versicolor and the virginic because those are kind of near each other. And I basically got what I expected. I got about 10% failure. And the software that we usually use to do this only gets about 2% error. So it wasn't that great, but it wasn't that bad either. especially if the other software didn't exist and I just needed to get started. So that was the result there. So you can go ahead and look through that example. All right, logic puzzles. Do you ever hear these logic puzzles, like if you know the LSAT type of examples, like you have to have like 4 people and they're wearing 4 shirts and they're eating 4 different kinds of food and you have to figure out who has what? It's that kind of problem. And you could also call it a rook problem. And I'm just doing a very simplistic one. That here's an example of a grid. You're going to put a 1 so that there's a 1 in every row or column. So in chess, it's so the rooks are not threatening each other. So a 1 in every row and column. As soon as you place a 1, you know the zeros go in the rest of that row and column. Okay. All right. So let's say if you want the silly problem that goes with this, you can watch my video. But let's say I've pre-solved it to this point. I know Alice is a female and she's wearing the red shirt, and Bob is a male wearing the green shirt. I know that the yellow shirt has to go on a male. That much I know. And of course, you can figure out the rest of the puzzle. Okay, but I want the sheaf to figure out the puzzle. And I want to give that information to the sheaf and see if I can get the sheaf to come up with the answer. Of course, this is what it looks like fully solved manually. So some early attempts, they just failed. I got very frustrated with this. I tried all sorts of things. And the problem ended up being that it was doing things like going less than 0, going more than 1, and I would have like 2 1s in a row. And I was like, what are you crazy sheaves doing, Michael? And he said, oh, why don't you try this magical command? So you'll see this magical command in the code. What this does is it forces the problem to live between 0 and 1. And that is specifically why we're using this optimizer. Because you can dump in any optimizer. He promises me if you have some proprietary optimizer you love, you can dump it in. Okay, but this is the default optimizer in this software, allows you to set bounds. And as soon as we did that, the problem was just totally fine. It just converged right to the right answer. Yeah.
Question. Is it possible to just kind of put another constraint or restraint as a sort of type?
Many things.
Like a logic type or integer type or something like that.
Yeah, but you can't run the operation.
I tried doing things like, okay, the rows have to sum to 1. The columns have to sum to 1. Okay, they have to multiply to 0. Oh, wait, but then it just means it has to be 1 0 in there. Like I tried all sorts of ways to force it. And he's like, do that. And it fixed it. I was like, what? Just that one line of code and it fixed. I got rid of all these extra conditions I had added that were just like totally useless at that point. Okay, so this is if you guys want to practice this kind of thing. You have a question. Oh, Bobby has a question too, right? Oh, you have a question.
I have a question. Okay, so sorry, can you set bounds like 0 greater than 0, for example, like just yeah, okay.
This particular problem, the only answers could be 0 and 1.
Yeah, of course.
And so we're getting back to this thing, like, why can't I just tell it only be 0 or 1? I don't know which slide I tell you this. I'll tell you now. The optimizer has to be able to slide. It can't just jump. It won't find the answer unless it can slide smoothly between the wrong answer and the right answer.
Right. Okay.
All right. So that's just why I picked 0 and 1.
Yeah. Okay. Okay.
Sorry, I'm just curious why you're multiplying the bounds by 16.
Oh, I'm sorry, because it's a 4x4 grid. And so in Python, this means I want 16 of them. It's safe typing.
Okay.
Yeah.
Okay.
Python magic. Good question. Okay, cool. So if you want to practice, do a 5x5 grid. And let's just assume A has to be 1. So like you have to match, so you make this grid with a Brooks problem. A has to be 1. G has to be 0. There's a rule B or C, or both, right? Or means either or both. And then some rules D exclusive or F, D exclusive or E, and E exclusive or G. So if you have those conditions, it's enough to solve the problem, and you can play with that and see how, say, if you have fun doing that puzzle. Any questions? Okay, next example, shout out to our alma mater. This guy is Julian Cole. He is no longer alive. This guy is still alive and well, and he was my teacher. And we studied asymptotic expansions. Woo, fancy stuff. But the problem I'm going to give you is just really simple. So the idea, just to tell you what asymptotic expansions are about, if you have a bug on your windshield, how come you're driving along and the bug can just sit there and stare you in the face? That's why, because like there's something called a boundary layer right at your windshield, there's no wind. But if you go a teeny bit above, there's a lot of wind. So the bug just sits there inside the boundary layer and smiles at you. So that's why I have that example. Okay, so what I'm going to do instead, again, my typical thing is I make a problem I know the answer to and then see if the software can do it, right? So I'm going to join these two, like this is like a sine wave or as a cosine wave, and then a parabola, because I did that so that they have the same slope and they have the same location at here. And then I'm just going to go between the two zeros. So I'm actually going to just take this piece of the parabola and this piece of the cosine curve, and that's going to be the solution to my problem. And so the way I'm going to do the problem setup is on the right side of the problem, it's going to be actually the cosine curve. Maybe the picture is backwards, I don't know. But anyway, they have to match at 0. So these two things have to match, but I don't say what it has to be. They just have to match. And then I put a 0 on the two ends, and the differential equations are just based on, like, again, I started with the solution and worked back to the problem. Okay? Make sense? Okay, right. So the way I'm going to code this up is P0 is that center that has to match. And all my arrows are going to go out. And all these cells are going to look the same, except the one on the end is going to look a little different. It's only going to have X, Y data. The rest of the cells are going to have X, Y, and Y prime. And I'm going to use this little bit of numerical analysis magic to hop from one to the other. Just a very basic numerical process. See if I can. Yeah, Taylor series with a little bit of mayonnaise. Okay. It's the 1.5. This is because it gives me better results than if I put a 1 there. Yeah, you know, you can do that. Okay, so then if you want to go backwards to the left. So the reason I wanted to do this is I wanted to have two different step sizes. So on the right side of the problem, you have one wacky step size and a different wacky step size on the other side of the problem. Okay, and so normally that's kind of a pain to do that. But the sheaves actually take care of that very nicely. And of course, in real life, you would use a script to generate that. I probably did use a script to generate. I don't remember, because otherwise you're going to type all that out and you're going to make mistakes. So you're going to write a program to write a program, and that's a standard sign. That makes sense. Because otherwise you're going to type it all wrong. Okay, results I got was the calculated solution. You see was not quite smooth at the bottom, but it basically looks like the theoretical solution. So this is just the error term. You can see that the worst error is 0.1, but right there where we saw it, it was bad. So at the join point, we got the worst error. Okay, so that was what the result looked like. Here's a problem for you if you want to solve it. And if you do, I gave you all the things you need to know to solve it. And I already did it. And so this is what you would get. This is what the theoretical answer should look like. This is what you will compute using the sheaf. And this is what your residuals look like. Okay, so if you want to have that fun. All right, now just some practical tips. And when you're building stuff, so I kept running up against this. I'm like typing things in and I'm thinking, I would really like to peek at what I just typed so I can see if I did it right. I mean, I know I could just look at what I typed, but I'd like to just have the code echo back to me and reassure me that what I typed is what went in. And so here's some tricks. You can coax almost everything back out of your code except the functions. You can use the functions you created, but you can't see them. And that is Python's fault. It's not Michael's fault. But you can actually use your function to verify, just to sort of reassure yourself that you put the right function in there. If you want to list all the node names, you have two different ways to do it. You can use the one that's native to PySheaf, get cell index list, or you can do sheaf nodes. That's from NetworkX. So as you can see in the documentation, that some of the stuff is native to the software what Michael wrote, and some things are pulled in from other packages that are read in. So this is built on top of NetworkX, so you get everything that you would have gotten from NetworkX already comes down. But this one explicitly is called out in the documentation because everything that's relied upon in the code gets brought out separately and explained in the documentation. Okay. If you do a get cell extended assignments, it will tell you all the work that's being done in maximally extended, which we will discuss after lunch, what's happening there. But the deeper you are from the top, the messier it gets. And if it's really messy, it'll just make an explosion on your screen. You might not want to see it. Okay. Get coface. It'll look something like this. You'll see a lambda function. It'll just tell you where it is. So you can use it and you can see where it's being stored, but you can't see it itself. Okay. That's what I just said before. So I'm just saying it again. If you want to look at the input tag type, this is a piece of the, this is a little bit of nuance we haven't discussed yet about when you're programming it, you have to define what size your data is or what dimension your data is, but you also have to give it a label because you might have like two different kinds of data that are the same dimension. So you have to specify on each node the dimension of the data and you give it your own made up name, but it's consistent throughout your code. So if you call it like M3 and you always, you know, your three-dimensional vector is always M3, then you call it M3 everywhere. So you make up your own thing on the fly, but then you have to be self-consistent. And so this will come back and tell you what tag you put on that node. And all these guys are from NetworkX and they work the same as they would, the in degree and the out degree. So you're like, how many arrows are coming in? How many arrows are going out? And edges is like altogether, how many edges, both the ins and the outs. So all that information you can get from NetworkX. And the documentation includes all these and more. I just wanted to give you the top hits in case you wanted a quick reference guide. Okay. So this is because when I was working on these, I was like, I wish I had a list. So now you have a list. Okay. Main concepts, sheaves are not magical. You can still have poor model using sheaves. You can sometimes get a decent answer quickly, nonetheless. It may not be the best answer, but it's possibly better than the current reigning top answer. You should probably use scripts to generate parts of the sheaf, especially if you have tons and tons of nodes. Okay. You don't need to generate any part of the sheaf that you're not planning on using. That's kind of a little nuance. So if you're planning on traversing like a really complex structure, but you know you're not going to be this like Rubik's Cube. Like say we want to talk about Rubik's Cubes and each node is a state in a Rubik's Cube. There's like millions. I'm not going to write that. But if I know I'm only going to be traversing part of it, I can kind of build it on the fly as I go. So that's allowed. Okay, but you just have to, keep, I have not done that, but the point is the program allows you to build out the sheath as long as you build the node before you need it. Does that make sense? Because I said before, build the whole sheaf and then put the data on. And I'm saying you don't really have to. There's times when it doesn't make sense. Okay. If we find ourselves needing to use real values rather than Boolean, so we find ourselves, I already said this one. You need to use real values to slide between Boolean values. It's because of the way the optimizer works. You can't just jump between discrete points. And this is part of the characterization of why is it that I keep running into issues when the problems I choose to solve have Boolean valued answers. And the answer is because the optimizer requires that there's smooth functions underneath so that it can find the optimized answer. Okay. Set bounds sometimes helps. Looking at what you're building can sometimes help. And it's the last slide, and we're only a couple minutes late. Good.
All right, let me take the microphone.
Yeah, so I have like a two-step back question that might be stupid or not, we'll see. So I just wanted to get it straight in my head, so I will try to reformulate what I think a sheaf is in this context and what PySheaf does. Mm-hmm. So as I understood it from the whole thing, PySheaf doesn't actually do anything in a sense. It doesn't calculate anything. It's not an algorithm. It's more of a reformulation of a problem that we have. So it connects different parts of like the data that we have. We give some constraints, but then it chops it up into like smaller problems, and then basically runs the calculation that the optimization method that we have is. So for example, it just cuts it up into smaller linear models and just runs those linear models and gives us the results just presented in a form that is reflective of the scheme that we put it into it. So in a sense, we could just go and write a bunch of linear models by hand, and we would get the same output. Just PySheaf helps with like structuring and conceptualizing it and putting those constraints, but it doesn't like actually, in your words, put any magic in it.
Okay, entirely correct with one comment. Does not have to be linear. Yeah, you said linear, it does not have to. Yeah. Yeah. Well, yeah, PySheaf helps you organize these calculations. And empirically, I've found that the process of organizing these calculations when the models are complicated is actually difficult to put into practice. And this makes that much, much, much more attractive. Yeah, cool. Okay. One other little comment about, yeah, as the microphone is moving, I'll make a comment. Part of the real valued and sliding values issue is due to the choice of optimizer. There are optimizers that can handle Boolean value data. We're not using that because we wanted to use the same optimizer for all our examples. Okay, yeah.
Just a micro comment. I mean, category theory actually is really all an insane structure. What you said is correct. I mean, PySheaf doesn't really do stuff. It highlights the structure you have there.
Yes.
And then often the solution, oh, then this is the solution right there. But you don't see that.
Yeah, category theory is very much like that. Which is why it's sort of infamous amongst mathematicians when mathematicians are being derisive of category theorists. They will say it is abstract nonsense, and it is, yes, that guilty as charged. Okay. One more?
Hi, sorry.
Oh, cool.
I just have some basic questions about the last example. So if you go back several slides,
Oh.
this cells to the right and cells to the left.
Yes.